So today we're happy to have Rachel Houtz back, our former student, who's going to tell us about discrete Goldstone bosons.
All right, I'm very pleased to be here with you all virtually, and I'm going to tell you about some work I did in collaboration with my collaborators at the IFT in Madrid, Belinka Vela and her PhD student, Victor and Guida Villeta, and also with the postdoc Pablo Quiles, who's now at UC San Diego. And if you're interested in more details, you can see our work on the archive. Sorry, one second. There we go. Okay, so a question that is pertinent to some who may be interested in problems of naturalness are what are the ways in which you can separate the scale between the mass of some scalar in your theory and the scale of new physics? And one very popular method to do that is to identify the scalar as a pseudo-Goldstone boson. And pseudo-Goldstone bosons have this nice property that their masses are technically natural. And by technically natural, what I mean is that if you have a theory with some approximate symmetry, so here I've shown a pseudo-Goldstone boson potential that's slightly tilted, and the mass of the pseudo-Goldstone boson is light because it's along this tilted direction that's tilted very slightly when you compare it with the scale of the theory, which is something more like the mass you would get in the radial modes. This particle is very light, much lighter than the scale of new physics, but it can be tuned. It doesn't feel tuned that it's so small because as you take the parameter that controls the mass to 0, you find that the theory gets an enhanced symmetry. So the mass of the pseudo-Goldstone boson goes to 0, and you have a true Goldstone boson. And then it's exactly massless, and the theory is enhanced by some symmetry. And so this is what we mean by technically natural, that the small parameter responsible for the non-zero mass can be small because as it gets closer to 0, you get more symmetry. And then generically, you find that pseudo-Goldstone masses, so long as you have this breaking parameter, can be very, very suppressed compared to the scale of new physics because they're suppressed by insertions of this breaking parameter. And this is a fine story. But some things that might feel a bit maybe unsatisfying about this is, in particular, the value of y break is kind of arbitrary. Like naturalness arguments just tell us that it has to be small, but it doesn't tell us that it has to necessarily be there. Like, why does the theory slightly broken, and what controls the exact value of this breaking parameter? And so this is one of this is one sort of motivation for looking at discrete Goldstone bosons. And another is that discrete symmetries may be the most fundamental symmetry of quantum field theory because we know that they're more compatible with gravity. For example, there's some old, very well-cited papers claiming that continuous global symmetries are compatible with gravity, whereas discrete symmetries don't have these issues. And also, discrete symmetries have this interesting property that they tend to be able to enhance masses of pseudo-Goldstone boson fields. And this was first introduced for axion-like particle pseudo-Goldstone bosons. And there's some papers by Hook and some papers by some of my collaborators that use in discrete Zn symmetries to suppress the mass of the axion and to make it much, much lighter than what you would expect from the typical QCD axion mass arguments. And I can give you a quick example from this, that I've lifted this plot directly from the paper of my collaborators, which is, so if you have a typical QCD axion, and let's say that's potential that's generated by QCD confinement that explicitly breaks the Peccei-Quinn symmetry, you might expect the axion to have a potential that looks like this blue line. But if the QCD is related, if there are multiple mirror worlds of QCD related by some Zn symmetry, and this Zn symmetry is set up such that there is a phase shift between these various contributions to the axion mass, you find that these contributions can cancel, and the axion mass is actually dictated by this total potential, this orange line, this orange curve, which is a much suppressed axion mass, or much more suppressed axion mass. And as you increase n, so this is n equals 2, if you go to n equals 3, you get even further suppression on the axion mass. And so these two ideas that this idea of discrete symmetry being useful in suppressing the mass of pseudo-Goldstone bosons and maybe allowing for a larger separation between the mass of light scalars and the mass of the scale of new physics, motivated us to look a little bit more closely at discrete symmetries. And one discrete symmetry that I'll talk about quite a bit in my paper is A4. So we're going to look going beyond just Zn, like what can be done with non-abelian discrete symmetries. And I'm going to talk a little bit about this because I'm not really a discrete symmetry model builder. So to me, a lot of this was new. When we look at A4, because A4 is the simplest non-abelian discrete group that has a three-dimensional irreducible representation. So immediately you can see how that might be useful in flavor model building because you can put all three generations into an irreducible representation of this group. And you may hear like something that you hear a lot when you're looking at models with A4 symmetry is that A4 symmetry is the symmetry of the tetrahedron. It's also the symmetry of the even permutation of 4 elements. And so quickly, I'll tell you why those two things are kind of the same. The members of the group of A4 are the even permutations of all four elements of all even permutations of 4 elements. And so you can kind of really easily see how this is the symmetry of the tetrahedral. So there's various ways you can do even permutations. Like one is that you can, if you have A, B, C, and D, you can just do a cycle of A, B, and C, and that's an even number of permutations. And that corresponds to, on the tetrahedral, just rotating this guy about one face, right? Similarly, you can do sort of these. Is there a question? No, sorry, I thought I saw someone raising their hands, but never mind. If there is a question, just let me know. Similarly, you can do double flips. So you can like switch A and B and C and D. And this is just the same as doing a 180-degree rotation about a line that intersects two sides of this tetrahedral. And so adding all of these kind of covers all the possible even permutations of 4 elements. And so this is the A4 group. And so the irreducible, so now let's talk about it in a way that's interesting to model builders. So the irreducible representations of A4, you have some singlets, one trivial singlet, and then you have triplets. And triplets you can think of as a vector that can rotate in an SO3 space such that it's restricted to only sort of hit these corners of the tetrahedral. And in particular, we might want to know how to form singlets out of representations of this group. And one thing that's useful to know is that two of these triplets come together and form a singlet if you do a direct product. And then if you do a direct product of 2 triplets, you end up with triplets again, one of which, I'm just going to move this control panel to be out of my own way, but I don't think you can see it. So you end up with 2 triplets, one of which is sort of the one that you would recognize from taking tensor products in SO3, the anti-symmetric combination of these guys. And then another that's a property unique to A4, which is the symmetric. This is the anti-symmetric combination, and this is the symmetric combination of them, which we denoted as epsilon tilde, meaning that it's just element by element, only 1s and 0s rather than minus 1s and 0s, also known as DIJK in other notation. Was there a question? No? Okay. And so there's more than just A4. So really quickly, if you extend this, you can get to higher groups, right? So if A4 is the even permutations of 4 elements, you can get similar even permutations of 5 elements where you get this, and a geometrical interpretation that's like this 20-sided object. And then you can go to higher AN. Similarly, there are discrete groups that you can make up out of not just even permutations, but all permutations of some set of elements. And those are the SN groups. Okay, so now that we have a bit of a quick, brief overview of discrete symmetries, I can tell you a little bit about how they're useful in model building. And I'm going to rely on this model, this paper that was quite interesting by Hook and Friends, that introduces non-linearly realized non-abelian discrete symmetries and kind of like intriguingly raises some properties about how they can lower the mass of the associated pseudo-Goldstone bosons. So let's see this in action in an actual particle physics model. So let's say you have a scalar field and its potential is SO3 invariant. So it has some continuous symmetry and its potential that is non-linearly realized at low energies. And so then this SO3 symmetry, before we even get to low energies, it's already broken by A4 invariant Yukawa interactions. So some fermion carries this A4 symmetry with it. And those interactions One, these will look familiar to you now, right? One is an SO3 invariant interaction, which is where everything's contracted by the anti-symmetric tensor. And then one is A4 invariant, but SO3 breaking, given by this epsilon tilde tensor. And this guy will be responsible for anything that gives the pseudo-Goldstone bosons masses, since this is the SO3 breaking parameter. And so once you have spontaneous symmetry breaking, SO3 breaks to SO2. And so, rather than looking at this in terms of the field pi, you expand it in pions. And what Houtz found is that at leading order, the quadratically divergent mass contributions stemming from these YS, the Yukawa couplings that are associated with the totally symmetric combination, at leading order, they cancel, which we wouldn't expect because these are SO3 breaking terms. But we find that quite nicely that, the first contribution, this one loop Yukawa interaction, plus this one loop Yukawa interaction and Bev insertion, these guys will cancel. And this is similar to little Higgs models. And so the question we wanted, and so this is like Hook's introduction to how these non-linearly realized symmetries enhance the suppression of the mass of the pseudo-Goldstone bosons, the masses of the pions here. And so the question we wanted to ask is, how general is this? Is this an accident of this particular model, or is this something that speaks very generally about discrete groups? And Hook drew some of these conclusions in his paper as well, but we tried to stay very general and not rely on any particular model to sort of examine these effects. All right. So now I'm going to speak more generally, now that I've shown you one example of a model where this discrete symmetry sort of accidentally arranges for some cancellation and a suppression in the pseudo-Goldstone boson mass. So let's talk very generally now about what these discrete groups can do. So let's consider a general scalar field in an irreducible m-dimensional real representation of some discrete group. And then this field satisfies a nonlinearity constraint, or in other words, the field takes a vev. And so phi t phi equals some f squared. And that reduces the number of degrees of freedom by 1, resulting in m-1 light spin 0 particles, which we call discrete Goldstone bosons. And if you don't believe that a discrete group can guarantee the existence of these discrete Goldstone bosons, instead, maybe a more comfortable idea is to consider that this discrete group D is embedded in a continuous group G, and G is broken down to D explicitly. And so these discrete Goldstone bosons are simply a class of pseudo-Goldstone bosons that are enhanced by this extra discrete symmetry. All right, so now let's look at an EFT for these discrete Goldstone bosons, and we're going to get a little less general and pick a discrete group. We're going to pick A4 again, the one we've already been talking about. And so if we want to talk about a potential that can be formed that's A4 invariant, we have to look at the primary invariance of this potential. And so it turns out that discrete groups have some really convenient properties. One is that any potential that's invariant under A4 is a function of 3 primary invariants. So there's the quadratic invariant, which is also SO3 invariant. And then there's 2 other invariants that are symmetric under A4, but break SO3. And that's this triplet and this quartic combination of fields. There's also like a quick caveat, there's something called a secondary invariant. So while the invariant potential can be written as a function of these 3 primary invariants, it can't be written as a polynomial of these 3. And so in order to include, if you want to write the potential as a polynomial of invariants, you have to include a secondary invariant, which is this I6. Just a quick little bit of a caveat there. All right, so now if we want to write something that's a potential that will eventually generate interactions for pseudo-Goldstone bosons, that means that we can write them as a polynomial of I3, I4, and I6, since these are the invariants that break SO3. And we can now expand this potential out. And then we can write, now we can write a full potential, like some tower of operators, where now I'm including, now I'm writing invariants that aren't necessarily primary, right? So I7 means some combination of like, say, I3 and I4, such that it's dimension 7. And then you can go up like C8, C9, up, and and encode all the interactions that could affect the masses of these discrete Goldstone bosons. And as long as we're below the scale of spontaneous symmetry breaking, which we'll call lambda, lambda is about less than or equal about 4 pi f, the nonlinearity constraint holds. So below this scale, the I2 invariant is just equal to f squared, so it's non-dynamical below that scale. So we only have to consider these invariants and higher. So now we have the most general potential for these discrete Goldstone bosons. Yes.
So it's also true, isn't it true that the group S4 of permutations of 4 objects is also, it's not a subgroup of SO3. Okay, never mind. Never mind. Go ahead.
Oh, let me see. I might have that on that slide. Let's see. S4 looks like a subgroup of SO3 to me. I think it is.
Yeah, but it's not but that's right. But it's not, but A4 is not contained in S4, is it?
I think it is. It is, yeah, but it's smaller. It is, yeah, but it's smaller. Yeah.
Okay.
So A4 is like more middle.
Okay. Yeah. Okay. Thanks.
Yeah, so I'm actually not going to talk about any of the SN groups. There is some in the appendix of our paper if you're curious. There's not too much more meaningful like results that come from them, but we did look at the pheno for some examples of S4 or one example in our paper. Okay. All right. Okay, so now we've written this general potential, but it's so general, it's hard to say much about it. For example, if all of these coefficients C and hat are order 1, then all the terms in this potential will contribute equally, and it's really hard to guess what interactions follow from the symmetry. But it's very easy, like without losing too much generality, to arrange for the lower order terms to dominate. So if we assume that these operators, especially the higher dimensional operators, are generated, like, so maybe even this potential of this potential, which is even active above the spontaneous symmetry breaking scale, it still might be some low energy effective theory. In fact, if we're including these higher dimensional operators, it likely is. And all of these operators are maybe generated by some interaction, like, for instance, the 4-leg operator or the many-leg operator, there's a ... here, could be generated by maybe some fermion running in a loop or maybe some scalar running in a loop. And every time one of these legs shows up, there's some insertion like epsilon. It's not so difficult to arrange that these C and hats all go like this insertion raised to the n. And so it's not too difficult to arrange for the lower order terms to dominate by just assuming this epsilon is less than 1. Still, everything we've said so far really only has one scale, f. So if we're a little bit less agnostic about the UV theory, we can introduce a scale that's not f, which is useful for naturalness, because if everything's tied to f, it's hard to argue why anything would be separated from it. And so let's take this idea a little bit more seriously. Let's say that these higher dimensional operators are generated by interactions, and that the particle that mediates these interactions is only active at a scale m. So for example, let's assume it's a fermion with mass m. Now we can really estimate these C and hats, right? So we expect that this fermion has some interactions with the scalar field, but any interactions that are going to give it a higher dimensional operator above 4 is going to come with some 1/m suppression. Every insertion will come with some coupling. And we can just sort of work this out and estimate the size of the C and hats. And so now we can say, given this sort of this UV completion assumption, we can say that the C and hats are going to scale like lambda over n to n minus 4 times the Yukawa coupling raised to the n. And so now it's we can say that the higher dimensional operators, n greater than 4 terms, will be just subdominant so long as either this Yukawa interaction is less than 1, so it's perturbative, which is a pretty mild assumption, or m is greater than lambda. So there's just 2 scales in your theory. And a caveat, A4 is a particular case because A4 has two operators that aren't higher dimensional, I3 and I4. If you want I3 to dominate, just for simplicity, you can't rely only on m being greater than lambda. You have to assume that the Yukawa coupling is perturbative. So we're still just looking at the linearly realized theory. So this doesn't say too much about the masses of the pseudo-Goldstone bosons, but anytime you have something that generates a mass for the pseudo-Goldstone bosons or the discrete Goldstone bosons, anytime you have a mass that generates that, anytime you have an interaction that generates a mass for them, it can't be proportional to I2, because anything that's proportional to I2 is going to be non-dynamical by the nonlinearity constraint. And so any interaction that might look something like this, it has I3 or I4 combinations, but at the end of the day, its overall contribution is to I2. These are going to be rendered harmless by the nonlinearity constraint. And in fact, you can usually see this because at the end of the day, many of these will be SO3 invariant. And so they shouldn't contribute to the discrete Goldstone boson mass. So anything like this is non-dynamical. And that's going to be important for understanding. That's going to be important for understanding the contributions to the discrete Goldstone boson, even if like there's interactions sort of in the middle that break SO3 via the I3 and I4. At the end of the day, if they contribute to I2, they're non-dynamical if that's the full contribution. And so these can't generate a mass term for the pions, but other invariants can. All right, so I still haven't expanded this potential in terms of the low energy fields. I've only talked about the scalar field, that's the linearly realized scalar field, if you will, up until this point. And so this is a complicated question because we're trying to stay as general as possible. So in general, I said that this potential that's invariant under A4, we know it's some function of I3 and I4. If it generates interactions for the discrete Goldstone boson, so we're saying at low energies, I2 is non-dynamical. So this is a function of these two things. You can write I3 in terms of the fields, and it's some complicated shape, and I4, and where the minima are going to be for this overall potential kind of depend on how these two are combined and which one's the deepest minima. But we can actually still use symmetry to say more about this. So if we want to minimize this potential and expand out these fields, we can just use the chain rule to say something about the minima, right? So if you just take the minimum, the partial derivative of v with phi, and you just expand and use the chain rule, so you insert the invariance in between, you'll find that this term will depend on the particular form of the potential, so how the potential combines the invariance. But this term here will depend on the structure of the invariants themselves. And so this term depends on the symmetry. And if either of these are 0, we have a critical point. So there's a class of critical points that we can talk about that only depend on the symmetry. And so we can classify these as two different types of extrema. One is a model-dependent extrema. So the position of the minimum depends on a specific combination of parameters in the potential. Like an example of this is the standard model Higgs potential. It's the position of its minima depends on the mass parameter and the quartic coupling for the Higgs. But the minima we're going to be talking about are natural minima, so they're extrema of the invariants themselves. So some nice properties about them is that we don't need to talk about any specific combinations of couplings to classify properties of the discrete Goldstone bosons. They only depend on the discrete symmetry. Also, the reduction in rank of the Jacobian indicates that at these minima, there will be preserved symmetries. So they'll have some particularly generic properties at these minima. But there's no guarantee that the natural minima are the global minima, that whether or not it is depends on the specific form of the potential. So the nice thing is that there's kind of a way to visualize this. So remember the nonlinearity constraint means that the space spanned by I3 and I4 is bounded because we know phi1 squared plus phi2 squared plus phi3 squared has to equal f squared. That bounds the space. And so that means we know exactly where these minima are going to be because any trajectory, as you vary the fields, you change I3 and I4, and you can just sort of map out these trajectories. At some point, they have to reverse at the boundaries. And so this derivative is forced to change signs. And so these the boundaries of this manifold. And if you fill this guy in further, you get a full manifold. The boundaries of this manifold are going to be the positions of the natural minima. And at the edges, or where the edges meet, the points will get sort of maximally natural extrema. So extrema that are always there regardless of how you combine the invariants together to form your potential. And so the nice thing about these maximally natural, we call them maximally natural because they don't depend on the coupling constants and the potential at all. They're always critical points. And they are going to preserve the largest subgroups of the discrete symmetry. And so for the rest of the talk, I'll focus on these natural minima, just to get a general sense of the behavior of discrete Goldstone bosons. But again, caveat, there's no guarantee that natural minima are global minima. I would argue there's also no guarantee that this one specific point in the bulk is the global minima, but whether it's any specific point in the bulk, of course, that's very possible. But that's not what I'm going to focus on. All right. So we can actually find the preserved subgroups, and they're the group of transformations that leave the positions of the extrema invariant. And so we can just write, we could just do this analysis and like find these points, right? And on this manifold, we've written them as A, B, and C. And we'll find that that A will always be a saddle point, so it's not very interesting for it's not an interesting choice to expand the potential around and find the properties of light fields. But B and C can be minima depending on the signs of the invariance in the potential. B or C could be a minima. And so we'll look at B and C, and at point B and C, the preserved subgroup that's left is a Z3 symmetry. And so we can just plot this guy out in space. So if we have phi1, phi2, and phi3, and I highlight point B in red and point C in green, these red points are the B minima, and C are the green points are the C minima. And you know, but you can see this nice tetrahedral structure. So A4 is manifesting again there. And so now finally, now that we understand the position of the minima, we can finally talk about the discrete Goldstone bosons very generally, and we're going to expand them about the minima. And then if we want to write these, this is I3, and this is a typo, this should say I4. I3 and I4, now we can write them out in terms of pi1 and pi2. This is the first way we did this, and at first it was very confusing what all these various minima and maxima are, but now we have an understanding of them from the point of view of the symmetry, that there are some of these particular bottoms of these potentials are more are kind of more natural than others. All right, so now that we can pick one and expand, we can now write discrete Goldstone boson fields. So we can write the I3 invariant, and we can just expand it out like this. And we can also write the I4 invariant, and it'll be some large expansion because now the pions are nonlinearly realized. This is coming from this exponential expansion. One thing that is kind of nice is that the Z3 symmetry is manifest in the low energy potential. You can see it right away by noticing that if you look at the invariance of Z3, there's a quadratic and a triplet invariant of Z3. You'll notice immediately that every term depends on either one of these two invariants. And a prediction of this symmetry is that you'll get degenerate discrete Goldstone bosons. And this is actually something that Hooke missed. He calculated the mass ratio of the two pions in his theory, and he didn't properly canonically normalize his potential, and so he found a mass ratio that wasn't 1. But if you do this right, you actually find that there's this symmetry preserved in the minimum and his minimum as well, and you find that they should be degenerate, and that's another reflection of this Z3 symmetry. And so you find that at this minima, A4 spontaneously breaks to Z3. And so now we can talk a little bit about the mass protection. So why this leading order SO3 breaking guy vanished. And basically it comes from the fact that anything that generates mass for these pions, it has to come from something in the high energy theory that's an I4 or an I3 invariant, right? So basically, if it's an I4 invariant and so this is now the linearly realized scalar field here. If this is generating the mass of the discrete Goldstone bosons, when you then spontaneously break SO3 to SO2, and you end up with your pseudo-Goldstone bosons, you need at least 2 insertions of the Yukawa coupling here to get your leading order contribution to your pseudo-Goldstone boson field. Similarly, you could get if you put a mass insertion for the fermion, you can get a triplet interaction in I3 invariant. But then you need a mass insertion and a Yukawa coupling to generate the leading order contribution. And this is exactly why, yes. What's up?
Sorry, sorry, I should have asked before, but maybe I missed it, but are you saying that there is no minimum that breaks SO3 but preserves all of A4, or you're just not considering those minima, or what's the situation?
I think it would be hard because I'm not sure what continuous group do you think A4 might be embedded in? Then it needs at least, if you're thinking of rotational symmetry.
It's not a subgroup because it's not a subgroup.
Yeah, it's not a subgroup of SO2.
Sure,
Yeah.
you're right. Yeah. Okay.
Yeah.
Yeah.
Yeah, so yeah, and actually like that's a good question because I think I think this comes up a lot when I give this talk, is some people think that SO3 broke spontaneously to A4, but that's not the case. So A4 is like the linear, that's like the UV group, if you want. We explicitly break SO3 to A4 in the high energy theory. And then when we spontaneously break to SO2, from the discrete point of view, A4 spontaneously breaks to Z3. So A4 is like the high energy group. All right. So anyway, back to what I'm saying. So this is exactly why the leading order contribution to the pseudo-Goldstone boson mass, even if it's coming from interactions that break SO3, this guy is guaranteed to cancel always because this only has 2 insertions of the Yukawa coupling. So this has to be generated by something like an I2 invariant, and the I2 invariant is non-dynamical. And so this exactly explains how the discrete symmetry kind of enhances this cancellation boson mass.
I got confused by.
Yeah.
So basically, let's say when there is a continuous symmetry spontaneously breaking to something, we say that Goldstone boson. But are you trying to say if there is a discrete symmetries that are spontaneously breaking, there are also Goldstone boson associated with the discrete symmetry breaking?
I'm not making that claim. So I think at the very beginning I said you can think of it that way. I think of it that way because I think it's a useful way to think about it. But you don't have there's no such thing as a discrete Goldstone boson theorem or a discrete Goldstone theorem.
Yeah.
And so a discrete symmetry alone, like if you're being very formal, isn't necessarily enough to guarantee the existence of these light states. But I think all of us would be comfortable with saying that an approximately broken continuous symmetry leads to pseudo-Goldstone bosons. And this is just a class of pseudo-Goldstone bosons, right? Because the A4 lives inside SO3. So you can think of SO3 as approximate, right? An approximate symmetry, and the A4 being the exact symmetry.
I mean, is it
Okay.
correct, following up on that, I mean, is it correct to say, this is my understanding, so I want to check in, that Y's are, you're assuming that these Y's are small parameters, and that guarantees that the explicit breaking from SO3 to A4 is small.
Yes.
That's why you have a pseudo-Goldstone boson, is because in the limit Y equals 0, you just have SO3 breaking to SO2. And then you have some small explicit breaking is controlled by the Y parameters. Is that right?
Yeah, that's a perfectly fine way to think of it. Yeah. And in fact, so let me really quickly say why. Let's see, how do I say this? So in this example, it's not very clear, but in later examples, it's not that Y has to be small, it's Y raised to some power has to be small in order to guarantee, and you'll see that again in a different example, but you need enough powers of Y so that you generate something that's the first invariant that's not I2. So in A4, that's a bit trivial because the first invariant is I3, but later that will come in.
Okay.
Any other questions? All right. So I think now, given our understanding of how we parameterize this potential and how it's restricted by the discrete symmetry, we can understand why this cancellation was always guaranteed in Hooke's model, even though it seems sort of accidental because these individual couplings violate SO3. So they should be able to contribute a mass, but they're always going to cancel because they're proportional to this I2 invariant. But is that enough to fully protect your discrete Goldstone bosons? And maybe you're already convinced, or maybe not. And you might be suspicious because there's nothing that these I4 and I3 guys might make you suspicious. So we can give a bit of a straw man argument if you like, something you might be concerned about. If you believe in EFT, I think by now you'll be happy. But if you're a little bit worried, we can consider like maybe a counterexample, right? So now let's consider again that we have this theory where above the scale M, which is much higher than the spontaneous symmetry breaking scale, there's some fermion that generates all the interactions. Marcus, do you have a question?
Yeah, I do, sorry.
Yeah, please go ahead.
But before, I thought you gave an expression of I3 and I4 in terms of the Goldstones, and it started at quadratic order. So why is it then that you're saying that at one loop you do not generate linear terms in I3 and I4? Is that the statement? Or I don't understand. I guess I didn't understand. Why is it guaranteed that you get this cancellation? What was the argument?
So absolutely, this diagram is here and this diagram is here, but they will always cancel. And this comes from something I said along.
You're going to.
Yeah, so I
did
did explain why. So let me go. This comes back to this statement. Yeah, it's a bit separated. This statement here, which is that anything that generates something proportional to I2, the I2 invariant, is non-dynamical by the nonlinearity constraint. So I2 is proportional to F squared, or it is F squared.
And that's some fact about A4 group theory?
This is just the field takes the bev, right?
Why you only generate I2? Why you don't generate a linear term in I3 and I4?
So so all you can generate is I2, I3, or I4, right? That's all you have. That's what you get from group theory, right? So you can totally generate an I3 here, an I3 and an I4, and these guys can totally contribute to the mass of the discrete Goldstone bosons like this, but they require more insertions of the Yukawa coupling.
So I'm asking, why do the ones that don't have the additional insertions only give you I2? I guess that's the part I haven't understood.
Yeah, so let's see, how can I say this? So basically, in order to get an I3 has three legs, right? And our argument is that all of these interactions are being mediated by some fermion field, right? And in Hooke's model, it was done explicitly that anything that breaks SO3 is mediated by a fermion field, right? So if you just have two insertions of the fermion field, then you just get an I2 invariant, right?
Okay, thanks.
Yeah, does that answer your question?
Yeah, that does. Thank you.
Yeah. Yeah, and so like this relies on this assumption that that these guys are somehow generated by some higher field, but you might still be a bit cautious, right? Because you might wonder, okay, like what about can these quadratic divergences sort of show up in another way, right? So let's look at this theory above F, where all the interactions are generated by some fermion with a mass m, right? So these higher interactions are generated by loops like this. So at one loop, all the bigger than log divergent diagrams we can make are these guys, right? Which are proportional to I2 and they can't contribute to the pion mass. But below M, so that's above M, right? Like where we only have, where we don't have any higher dimensional operators. But as soon as you allow higher dimensional operators, so you go below M, you may be worried by diagrams like this, right? So you could have something that's got 6 legs and that's closed and that picks up a quadratic divergence through this guy, right? And you might be concerned that the C6 operator, when you do some matching onto the discrete Goldstone bosons, you might be concerned that sensitivity to this high scale M is maybe feeding in, right, through diagrams like this. And then this would source an I4, and we know I4 interactions like this do contribute to the discrete Goldstone boson mass, right? So you might be concerned about operators like this. And I put this slide in because, you know, we got emails about this. But if you believe our power counting, you shouldn't be worried about this, right? Because this C6, we can estimate its size and it's tied also to this high scale M, right? And so if we estimate the size of C6, C6 should always be suppressed by enough powers of M to give you like the right dimensions in your theory, right? Like this is coming from a higher dimensional operator and the M sensitivity cancels out. Right. And so this shouldn't be concerned. And maybe this is like a bit of overkill because if you believed in EFT theory, maybe you already wouldn't worry about diagrams like this, but we did get some questions. So I thought I'd put one slide in to sort of allay any concerns about that. And so let's look a little bit more about the phenomenology of these guys. One big feature is that that the one loop quadratic sensitivity cancels, and so they're not sensitive to the cutoff in a way that's like y squared times the cutoff squared. But they also have some other interesting features. And this is going to depend very much on choosing a minima such that we've chosen that A4 is spontaneously breaking down to Z3. And one phenomenological, one feature of the pheno is that we'll get degenerate pion masses guaranteed by the symmetry. Also, if we assume that the I3 operator is the leading term, so we assume that all these operators are generated by interactions and that we can say I3 dominates. And we also make some assumption, just sort of for minimality, that the standard model processes are unchanged, that anything in the standard model is uncharged under the discrete group. So it's just all in the BSM sector. We can say something about how these guys are produced. So just looking at the I3 operator, we'd see something like 2 pion production, 3 pion production, and 4 pion production. If we say that maybe this discrete symmetry talks to the standard model through some messenger scale that we can identify with M. And so because these interactions all stem from the same operator, there's a consistent pattern of production in these cross sections. So we can just calculate quite easily the ratio of 2 pion to 3 pion production and 3 pion to 4 pion production. And the 2 to 3 pion production might not seem very, very interesting, 64 pi squared, okay. But the 3 to 4 guy has a particular pattern, right? That has nothing to do with the that has nothing to do with the Z3 symmetry. Right, we have like 19 and 17 in the denominator here. And this is only a feature of the A4 symmetry. And that's kind of interesting, right? Because it's not so common that discrete Goldstone bosons, it's not so common that pseudo-Goldstone bosons can tell you anything about the full symmetry group above the spontaneous symmetry breaking scale, right? Like there's this there's this paper, this paper by Ian Lowe, right? This Adler's zero mode condition, that's it. And so typically, like for continuous groups, you don't just studying the pseudo-Goldstone bosons can't tell you about the high energy group, but for discrete Goldstone bosons, making a few minimal assumptions, you can actually learn about the A4 symmetry that's really only realized at very high scales. So that's one interesting property. And maybe we could disentangle this. So if you were to guess that these guys would show up in a collider first, there's like a lot of kinematic variables that you can use, or there's one kinematic variable, at least one, that you can use to disentangle the number of invisible states, right? There's this paper from way back in the day talking about this by sort of studying the tails of distributions like this MT, which is sort of similar to missing ET, but not quite. You can pick out n equals 2, n equals 3, or n equals 4. There's some possibility of disentangling multi-component dark matter in direct detection experiments, but everything I've seen doesn't really work if you have degenerate masses. So I'm not sure it's very promising here. But it would be really cool if we could think of something, because then maybe you could see these in like, experiments that search for ALPS or something like that. And then really quickly, so that's the example of A4, but I can give you an example for higher symmetry groups. And so I can go through that really quickly, and something interesting shows up when you look at A5. So you might get a bit bored now because it seems like the model's getting more complicated, but it's really not. Like I'm still talking about a triplet, like a 3-dimensional representation. I'm just embedding it in A5 instead of A4. So it's just in some slightly larger group. So rather than just being able to rotate around the tetrahedral, now it can go around this 20-sided object. And A5 also has 3 primary invariants, but those invariants now are different from the A4 invariants. In particular, and since I'm running low on time, since I think you guys have another talk to go to quickly, I'm going to go a bit fast here, but I'll just quickly highlight that there's the quadratic invariant, but there's the next level invariant is a 6-dimensional invariant, and the next one is a 10-dimensional invariant. So these are the 3 building blocks that can form the potential. And so that means that the most general potential for these discrete Goldstone bosons is going to start with higher dimensional operators, right? And the A5 symmetry itself forbids any operators that are lower than 6, except for the non-dynamical quadratic operator. And so all terms that affect the discrete Goldstone bosons come from higher dimensional operators. And so the masses of the pions are going to be more suppressed because they're going to be proportional to C6 hat. which has either more insertions of the Yukawa coupling or it's more suppressed by this high scale M, depending on your choice for the UV completion.
Sorry.
And you can do, yes.
Why are we interested in triplets specifically again?
I'm sorry, could you repeat the question?
Why are we interested in triplets specifically?
Why am I interested in triplets? I guess just minimality. So you could look at, I mean, it's the smallest ear-rep that has, you know, that's more than that has three components. I guess you could go into doublets. I don't know. I find triplets, I guess, a bit nicer because you can embed them in SO3 breaking to SO2. So it seems like a small thing that still has some interesting group theory. But that's my preference, although I wouldn't say there's anything too special about them at this stage. Does that answer your question?
Yeah, thank you.
Mm-hmm.
I have a follow-up. Do you think going to different representations would change what you're seeing? So the effects that you're looking at?
Yeah, so we have a few
zoo out there waiting to be found, or?
Yeah, so we have a few examples in our paper, and everything we looked at, we found in general, there will always be some degenerate set, and they're always the lightest set in everything we looked at. Although that might not be true for all discrete groups. In general, you can always, at least we put together a recipe for an analysis that you can always do for any discrete group, and that you can write it in terms of these invariants, and you can look at the maximally natural minima, and you can expand, and you can identify the preserved symmetries. And then you can do some phenomenology by making the assumption that the lowest dimensional operator dominates. So we gave a recipe in our paper, and we did a few examples, and we found some generic features, but didn't prove that they're generally true. But the one generic feature that tends to be true is that you get a lot of suppression if you're using a small representation in a larger group. So you'll notice when I'm doing A5, I'm still doing a 3-dimensional representation in a larger A5 group. And that's giving me this effect that we have these higher dimensional operator invariants as the only guys left. If you were to do like a higher, like if you were to do the 4-dimensional representation, you don't see this. All right. Any other questions? Okay. So again, like I said, we put together this recipe, you turn the crank, you find the natural minima, and you do the phenomenology, and you find that here in this case, you find A5 spontaneously breaks down to Z5, again, degenerate Goldstone bosons, assuming the I6 operator is the leading term, which is a way more general assumption now, because the next guy would be I10. You get another pattern for 2, 4, and 5 pion production. And again, you find a prediction for the ratios of cross sections that tells you information about the full A5 symmetry, not just the preserved Z5. And I'm just going to skip through this since I know you have another talk. I don't want to make you late, but I can just jump to the conclusion, which is basically what we did is we wrote down an EFT to really try and classify the behavior of non-linearly realized symmetries and their associated discrete Goldstone bosons. In particular, we pulled out a few features that are guaranteed to be present. One is that they will have an enhanced protection from quadratic divergences, and that this enhancement stems from the fact that the I2 invariant is non-trivial. So the typical story for pseudo-Goldstone bosons is that the one loop guy generates their mass, but anything that's proportional to the I2 invariant won't give them a mass. And so you always have to include higher insertions, so more insertions of the Yukawa couplings to get the next higher invariant, which can be as high as I6, right? Which requires then 6 insertions of the Yukawa before you get a mass for these guys. And that was the case for A5. And then for the case of A4, you just need 3 insertions of the Yukawa coupling. So that's why we're seeing this sort of accidental cancellation in some of these models. And we wrote down an EFT and classified their general features. And in particular, we found that not only do they have this suppression, but if you find them interesting, there's some sort of smoking gun signals to look for them. They'll have degenerate pions. That is a result of the low energy symmetry. You'll usually see multi-particle and visible production if you're assuming that the standard model isn't embedded in the discrete symmetry. And the cross-section ratios give you access to the full non-linearly realized symmetry, which is a lot of power because the low energy measurements will give you information about the symmetry is active at very high energies. Thank you.
questions?
Maybe a very simple one. And are you aware of similar work in the context of solving hierarchy problem using this kind of property?
Hierarchy problem, yes, that's what we're interested in doing one day, although it's not easy to put SU2 in a discrete group. Yeah, so some of these papers I put at the beginning were some of these early, at least the works I'm aware of. So Hook, right, in this paper here, he talks about using the ZN symmetry to enhance the protection of the axion mass, but he also has a section in this paper where he applies it to the hierarchy problem. He finds that it gets spoiled at one loop though. So like the one loop contributions sort of give it the wrong sign. But I mean, maybe there's more there if you go to non-linearly, if you go to not non-linear, to non-abelian groups. Yeah, unclear. But yeah, he does have a section in this paper about that.
Okay, so I think this is discrete symmetry about boson, scalar boson. What about the fermion? Do we have similar stuff for fermions?
What do you mean?
I mean, we know that that Goldstone boson called the Goldstone, right? That is a fermionic Goldstone boson. I'm trying to see if there's some similar stuff in that.
That's a good question. Yeah, I haven't thought about Goldstinos or like fermionic or like anything related by supersymmetry. I haven't thought in that direction. That's a good question, but yeah, I don't have much to say. I was only thinking of sort of the typical Goldstone bosons. Yeah.
Okay, never mind.
I mean, can I just kind of related to that? I mean, it looks to me like, because I was trying to think about this too, like if you wanted to use it for the standard model hierarchy problem, then it looks to me like it would be something very similar, or maybe it's identical, a generalization of twin Higgs. So in twin Higgs, you have a Z2 symmetry, right? So it's in a discrete subgroup, and there's a similar statement that the low order invariants that are invariant under that are accidentally invariant under the full group, and so you don't get the similar thing. You don't get the mass, and so it seems like you would have the same thing. The standard model is of course not a subgroup of the discrete group, but you just like in twin Higgs, the fact that the discrete subgroup is in some sense controlling the alignment. I'm not sure if I'm thinking about that right, but it does look very similar to me.
Yeah, so that could be the case. To me, I was finding that it's very difficult to do this because the spontaneously broken group, it has to already be explicitly broken to a discrete group, at least in the most direct version of this, like the one that I like Hook's model, for example, the one that I was using as an example. And so it's hard to use pseudo-Goldstone boson Higgs models directly because you don't want to break SU2 left to a discrete subgroup. That's the problem I was running into.
You need the unbroken group. You have SO3 to SO2. You can't embed the standard model in SO2. You have to be able to embed the standard model gauge group into the unbroken group, right?
Yeah, and then you don't
alignment. And so
and then you get something that's not so interesting. Yeah, I agree. Then you reproduce these models. Yeah, I see what you mean. Yes, then I agree. Yeah. So I'm not sure I see a way out. Yeah. So yeah, I'm not certain. I think it's like something I would like to think about more, but yeah, I wouldn't like to just reproduce the twin Higgs stuff. Yeah.
Well, I don't know. It seems like it's interesting because somehow the discrete group here is giving you is in a way giving you aligning the vacuum. You can think of it as aligning the vacuum in directions that are perhaps interesting. So that would be the twin Higgs mechanism does not solve the little hierarchy problem, right? In a way, that's what you're trying to do here. Ultimately, you're trying to make the, I don't know. Anyway.
Why do you say it doesn't? I thought that if you can have. What am I thinking of? I mean, I feel like I'm thinking of papers where, you know, twin Higgs basically introduces something like this. No?
Maybe I'm thinking about it wrong. Other people here have thought about this more than me. My impression was that twin Higgs by itself still has the V over F tuning. Am I wrong? I mean, the little hierarchy is not the mass, it's in the bed, right? For electroweak symmetry breaking, you can make the potential flat, but the problem is you need to make the bed smaller.
Hmm.
So maybe this discrete thing doesn't help either for that, I don't know.
Yeah, I'm not sure. I'll have to think about that a bit. Yeah.
Because you're flattening the potential, but the location of the minima, that is the scale V, right? That's the scale, and you want to make V small. Not, and the Higgs mass small. You need to make them both
Yeah.
small. Right?
Yeah.
And you're not shortening that distance.
Yeah, I see what you're saying. Yeah, so they can, they do have that price. Yeah, so I see what you mean. They do have that price of the tuning for when they can sometimes make the mass small, but then they have that extra.
But there are approximately, I'm exaggerating a bit, 8 million papers on twin Higgs, okay? So, I mean, so even though it doesn't solve every problem, I think it's considered to be, you know, an important class of models, because the V over F tuning is not so severe that you think this is completely dead. It might be interesting to see if these models give some interesting generalization with,
Yeah, perhaps. Yeah.
you know.
Yeah, you need the big quadratic coupling, right? Big enough quadratic coupling,
Right.
which breaks the symmetry. Do you have that in your model? Sorry,
So you can have a quartic coupling. So not in this model with Hook. But basically all you need to do is generate, see, where do I have some pictures? You just need to generate something like this, right? So when you say big enough, I'm not sure, because it will, if you're relying on Y being small, then the quartic will be smaller than the triplet interaction.
But
So
if
yeah.
you go back to your pictures, you know, you're flattening the potential, but you're not moving the minima closer together. So I think this by itself does not give you the big quartic or this small bed, however you want to say it. You need something in addition, I think.
Yeah, I agree. We're not moving minima closer together. That's
Can you
true.
go back to your the stolen plot
The stolen plot. Yeah.
at the beginning?
That's the one. where-
Lifted, okay. Here?
Yeah, lifted.
Yeah.
So this in the second plot, the minima are closer together than in the first plot. And as n goes to infinity,
That's
they
true.
become arbitrarily close together.
So that's true. That's actually another, I think that's one of the mechanisms in another Hook paper where he does that kind of thing, where he basically, yeah, you exactly break, you sort of break something down to a Zn, and n is very large, and so that gives sort of, you know, a full U1 rotation, for example, would be broken down to Zn. That forces the minima to be, you know, sort of F over N apart, right? And so then all you have to explain is why you're in one of the first few rather than the ones far away, if you have, you know, right?
Yeah, so I actually think maybe this isn't so bad, right? Because if you go to higher, it's the same story when you go to higher AN, at least from A4 to A5, is that like the position of the minima, like, you know, if you have like this, you think of like the sphere. I mean, unfortunately, it doesn't work like this. It would be nice if you could like take n to infinity and get SO3. I'm not aware that that's how it goes once you go above A5. But like A4, like you can only hit certain spots, and if you go to A5, you can hit more spots. But I don't think you have this nice feature of like n to infinity, like covering the whole sphere. That you do, like you have that from Zn and U1, for example. Like this goes, as n goes to infinity, you reproduce the continuous symmetry. And yeah, I
Mhm.
think in Houtz, he doesn't end up in the right. If I'm remembering right, he doesn't quite end up in the right minima, right? Like as soon as he includes the Coleman-Weinberg potential and he ends up in the wrong one or something. But it's been a while since I've read this paper. Yeah.
Just numerically, I don't think you need n to be very large. I think n, because d over f is like 1 over n. So you really just n of just a few, 4 would be fine for the, that's getting you in the right range for the little hierarchy problem actually already. The little hierarchy problem is pretty little. So,
Yeah.
So maybe 4 is twice as good as 2, like twin Higgs does something like 2, and some not crazily large discrete subgroup, A8 or S5 or something could, I don't know, might actually just work.
Yeah.
So you should write another paper.
Yeah, I mean, those are some great comments. Yeah, it's interesting ideas. Yeah. Or I could do what Hook does and write like 3 mini papers in one. That's what he did here.
Any other questions? And let's thank the speaker again.